All right, let's go ahead and get started. So, you guys have talked about the graphing stuff, inflection point, all the pieces of graphing. I felt like these were kind of some interesting questions about what it really means to have an inflection point somewhere. Let's look at the first one. In fact, let's look at the first one just by graphing it. So that's a pretty straightforward graph, I think. We know what x squared looks like. We know what the square root of x looks like. So if we graph it, we have on the left-hand side, it looks like x squared, so your usual upward opening parabola. On the right-hand side, it looks like your square root function, so like that. So the question remains, do we have an inflection point at the origin or not? Well, just looking, not doing any sort of analysis, just looking at the graph over on the left side here, is it concave up or concave down? Definitely concave up. For sure, it's concave up over here. How about over here? Looks to me like it's concave down, right? And you could either think of it as opening downwards or any tangent line you drew there would be above the graph. Some people like to think of it as like you're looking like at a top-down road map, and you imagine a car like driving along this road, and on this part of the road, the car is turning very, very slightly to the left, 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 and then right here we take a sharp change of direction, and we start turning right, 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 right. So that's another way to think about what's going on there. So we definitely have a change in concavity. The function's defined, and we do not have an inflection point. So this is 0, 0 is not an inflection point. And the reason why is because the graph doesn't have a tangent line there. Now, I want to be super extra clear. The function doesn't have to be differentiable for there to be an inflection point. The example of this is x to the 1/3, which we'll graph in a second just to remind you. So you don't have to be differentiable to have an inflection point, but you do have to be able to draw a tangent line at the point of inflection. And essentially your tangent line should be below the graph on one side and above the graph on the other side. Here, I think it's fairly obviously not differentiable at all, meaning we couldn't draw a tangent line if we wanted to. Again, you don't have to be differentiable to be able to draw a tangent line. Usually you do, but not always. So definitely can't draw a tangent line here. We have a cusp or a corner. I think it's a corner actually, not a cusp. Sorry, we have a corner, not a cusp. Apologies. To me, I don't differentiate very well in my brain between them. Um, how would you show it? Right, annoying. Right, exactly. I see the looks on your face like, how would you show it? I'd probably show it by showing it's no, see, that's a real graphically. I think this is actually the best way. I was like, maybe I would do a thing, but like to show it, you'd have to show it didn't have a tangent line at the origin. And I feel like the best way to do that is kind of graphically, right? It's not really easy to be like, you could show the limit didn't exist, or sorry, you could show that the derivative at zero didn't exist by showing the left-hand limit and the right-hand limit of the derivative weren't the same, which I guess would probably be sufficient because that's kind of showing it doesn't have a tangent line there because the slopes wouldn't be the same, but it's still kind of annoying. What about this other one here, which is a piecewise function hidden, which is, I mean, not that hidden. Absolute value, I think we have learned at this point, absolute value function is a piecewise function. It's just kind of, we don't write it that way. You can definitely write this as, well, if x is less than 0, the absolute value of x is negative x. because you want it to be positive in the output. So you get x times negative x when x is negative. If x is positive or 0, the opposite value of x is just x, and you get x times x. So this graph looks like negative x squared on the left side and positive x squared on the right side. So it looks like that there and that there. Concavity changes, and I do believe we have a tangent line there, right? The slope of the tangent line on the right side and on the left side and slope of the tangent line on the right side are both getting closer and closer to having a slope of 0. And at the origin, they exactly meet up and have a slope of 0. So this one definitely does. 0, 0 is an inflection point. I've definitely seen, oops, sorry. I've definitely seen this function come up before from instructors. Like it's kind of a neat example of a piecewise defined function that still ends up being like continuous and differentiable. So kind of worthwhile. But back to the other thing I said. So just to point out, right, this function I will say I won't show. So definitely g of x has a tangent line. It's the x-axis, y equal to 0 at the origin. And the concavity changes, right? It's concave down over here, it's concave up over here. So we definitely have an inflection point at the origin. What I was trying to say is this function is differentiable at the origin, right? What's the derivative at the origin for sure? I think it's 0. We can show it. Let's see. So if I wanted to show that this function was differentiable at 0, my function again is negative x squared when x is less than 0, positive x squared when x is bigger than or equal to 0. We look at our derivative, it's going to be negative 2x on the left of 0, positive 2x on the right of 0. And we can, just by looking at it, see that from the left and the right-hand side, if we get closer and closer to 0, we're going to get either a negative 2 times 0 or a positive 2 times 0, which is going to be 0 either way. I personally like to choose to wait to fill in where the equals goes, or if I get to have an equals, because if they're not the same as each other, the function's like not differentiable at 0, so you can't like say it's fully defined. But here we can go ahead and add in the greater than or equal to here and say, oh yeah, g prime of 0 is definitely going to be 0 because the limit as x approaches 0 from the left of g prime of x is equal to the limit as x approaches 0 from the right of g prime of x. And those both end up being 0, right? This is just the limit as x approaches 0 from the left of negative 2x. This is just limit as x approaches 0 from the right of positive 2x. And they both end up being 0. So that's differentiable. And we can see that there's a tangent line then because the tangent line just has a slope of 0. One more example, just to kind of say a little bit more about these weird cases where you don't get an inflection point, or you do get an inflection point, you feel like you shouldn't, or you don't, you feel like you should. This is probably the best example of a function that does have an inflection point somewhere, but the derivative and the second derivative aren't defined there. So here's our cube root function. It looks like this. Vaguely like this. And certainly, if we start looking at the derivative and the second derivative, our first derivative is 1/3 x to the negative 2/3, or I would probably prefer to write it as 1 over 3x to the 2/3. Certainly not defined at 0, right? F prime of 0 is undefined. Our second derivative, f double prime of x, well, if I take the derivative of this, it's going to be 1/3 times negative 2/3, which is negative 2/9 times x to the negative 5/3, or I might prefer negative 2 over 9 times x to the positive 5/3. And we can certainly see that the second derivative, even though it's undefined at 0, does change signs on either side of zero, right? If you pick a positive number for x, the second derivative is going to be negative. Pick a negative number for x. A negative number to the 5/3 power is still negative. So negative 2 divided by a negative is going to be positive. So it's concave up over here, concave down over here. No surprise based on the graph, right? It looks like it's concave up over here. It looks like it's concave down over here. And then this graph has a tangent line, a vertical tangent line of x equal to 0. And to be perfectly frank, I'm not really sure how you're supposed to see that without the graph. Like, I don't know, like if you didn't graph this and you just did this work over here, like, well, okay, the derivative is undefined at 0, the second derivative is undefined at 0, the concavity changes. Do I have a vertical tangent line there? I mean, I guess, okay, I guess I think I can think of what you, would that work? Here's what I think you would have to do if you wanted to see if you have a vertical tangent line there. The slope of should be approaching infinity from either side, right? The slope is definitely slope of my tangent lines on the right. Ah, yeah, okay. The slopes of these are getting closer to positive infinity. The slopes of these are getting closer to positive infinity. So if you had to do this non-graphically, I would say, well, even though f prime of 0 is undefined, let's take a closer look. If we look at the limit as x approaches 0 from the right of f prime of 0, it's the limit as x approaches 0 from the right of 1 over 3 times x to the 2/3. And that x to the 2/3 is always going to spit out a positive result, right? X squared, positive, doesn't matter what you do after that. It's always positive. So this is going to be a positive infinity, because we're dividing by 0. And on the other side, if we approach 0 from the left-hand side, it's also going to end up being a positive infinity because the negative number squared is positive and the key root of a positive is positive and it's still positive. So I guess you could say, well, since the right-hand limit and left-hand limit, even though they both don't exist, they're both getting infinitely large, and so you're getting this vertical tangent line. Whereas if one was like a positive, one was like a negative infinity, you'd have a cusp kind of thing going on. So this shows that we do have a vertical tangent line at 0, 0. And just for contrast, this function, g of x equal to x to the 2/3, does not. It looks like this, ooh, kind of like this, but better, does not have a tangent line at 0, 0. The limit from the left would be negative infinity. The limit from the right would be positive infinity. I don't think that's probably more detail than we really need, but I was thinking about it, so it's what I thought about. There's one other thing I was saying. Really, I think looking at the graph is the most useful thing, and you can typically tell basically whether if you're going to have an inflection point where the concavity changes if the graph is smooth or not. Right? If you've got pointy things going on, it's probably not an inflection point because you have a weird corner or a cusp. If it's not pointy, you're probably fine. But really, 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 this is why we focus on graphing, because the graph actually can tell you a lot of information instead of having to do all this other work. You look at the graph and be like, cool, there's an inflection point. I didn't have to do first and second derivative and take a limit from the left and the right and see if they're the same, right? I just could look at it. All right. Graphing. We should probably talk more about graphing. Have you in class yesterday, what did you only talk about graphing? Or I should say things associated with graphing, or have you started talking about L'Hopital's rule yet? No L'Hopital's rule. Okay. We might still talk about it today anyway, because it's a time-consuming topic. But let's do a few more graphing things. Let's look at something like, yeah, we'll do this one first. Let's graph f of x equal to Sure. 3x times e to the negative x. I should look over here too. So it's always the same process, right? We're always looking at the same things. Intercepts, asymptotes, first derivative stuff, second derivative stuff. I think I was looking at your teacher's, at least Lee's, like week 9 highlights, and I would say that their order of finding things for graphing is a little different than what I do, right? The way they've written it out is find the domain. Okay, fine, domain's important. Find the derivatives. I kind of wait to do that until after I've found the intercepts and the asymptotes, but fine. And then find the critical points using the first derivative, find the points of inflection, then find any asymptotes. Your teacher's not wrong. There's a good reason to wait until after you've found some derivatives to find the asymptotes. We'll talk about that actually in this example right here. So, well, let's go ahead and do it the way I like to do it because I'm the teacher. So, anyway, it's the benefit of being the teacher. You can do it the way you like. First of all, the intercepts. So let's see, y-intercept, we're going to find f of 0. It's going to be 3 times 0 times e to the 0, which is 0. That's your y-intercept. And an x-intercept, but there could be more x-intercepts. So we want to find the x-intercepts. Let's see, we set the whole thing equal to 0. And one thing I want to point out here is if you set this whole thing equal to 0, some people like separate the fact. I've seen people do kind of extra. Like people be like, okay, I'm going to set 3 equal to 0 and x equal to 0 and e to the negative x equal to 0. You shouldn't be setting 3 equal to 0. You know 3 doesn't equal 0. This doesn't give you anything. This is garbage. If you really wanted to, you could say 3x equals 0 and then get x equals 0 from that. And then over here, it's perfectly fine to think about this for a second, but e to the anything is never 0. E to the anything, in fact, is always positive. So just an aside here, e to the negative x is strictly greater than 0, no matter what you plug in for x. So definitely nothing here as well. So we only get the one intercept, the origin. Kind of boring. Oh well, such is life. Moving along. Vertical asymptotes. There shouldn't be any. And we know there aren't any because we don't see any of the telltale hallmarks of having a function with a restricted domain. Because really, 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 when you're thinking about where your vertical asymptotes might be, it's where your function might be undefined. Where you might be dividing by 0. That's kind of it, right? Not really. There's one other thing. You might be dividing by 0, or you might be taking a log of 0. But those are the only places where you get vertical asymptotes. And not even always then. So vertical asymptotes potentially come from something divided by 0 or the log of the 0. That's really, really it, though. I'm going through my head now. Was there any other exception? I don't think so. Yeah, no, yeah. No, no, yeah, that's it. Those are the only ways to get vertical asymptotes. You either have to be dividing by 0 or taking a log of 0. And sometimes not even then. If you come up with something else, let me know. I don't think I missed anything, but I would be happy to be wrong. Moving along. Horizontal asymptotes. This is the place where I do think your teacher might be right in that it's a good idea to wait until later because at this point, without L'Hopital's rule, we don't necessarily have a good way of evaluating the limit as x goes to infinity of 3 times x times e to the negative x. Because what this is called, if you plug in infinity, you're going to get 3 times infinity times e to the negative infinity. And e to the negative infinity is really, really, really close to 0. So this is essentially what we call an infinity times 0 indeterminate form. I feel like your teacher uses a different word. There was something else I've read that looked, I like their word too. And where'd it go? There was a different word. I can't remember what it was. No, indeterminate form. Okay, I feel like there was something else there, but I guess not. So I should point out, this doesn't mean infinity times 0. What this means is a really, really big number times a number that's really, really, really close, but not equal to zero. Because if it was actually zero, zero times something would just be zero. But it's not. It's a number that's really, really, really small, but then you're multiplying by a number that's really, really, really big. And so the result could be anything. That's why it's called an indeterminate form. Because whenever you happenstance upon something like this, the result could be literally any possibility, which is why we have to do stuff. So here we're going to leave this alone for a minute, and we're going to come back to wait until we graph it. Later on today, we will talk about L'Hopital's rule, and we'll do this example so we can kind of see how you do it with L'Hopital's rule. Okay, I'll kind of jump the gun here. I will point out this one, if you rewrite it as 3x divided by e to the x, it's pretty easy to justify to yourself that this fraction, the denominator really, really, really outpaces the numerator, right? If you plug in like 10, 30 is not that big. E to the 10th power is gigantic. 30 divided by e to the 10th is super duper small. This definitely goes to zero. But sometimes it's harder to just make that sort of internal justification that you can kind of see, oh, this part's bigger than that part. So it's going to be either zero or something really big if the numerator is the big thing. So let's go ahead and talk about the first derivative stuff. So I'm going to take my first derivative. My function again was 3x times e to the negative x. My first derivative is going to be, so when I have a product rule like this and there's a constant, you can pull the constant way out in front. I kind of think it's nicer to think of it as this piece is 3x and this piece is e to the negative x. So then the derivative of my first piece is 3 multiplied by e to the negative x, plus now my first piece is 3 times x, multiplied by the derivative of e to the negative x, which is e to the negative x times negative 1. So set that equal to 0, and then we factor as much as we can. We're going to factor out a 3e to the negative x from both pieces. We're left behind with a 1 here, and an x times a negative 1 there, so a negative x. Setting that equal to 0, we know that e to the negative x can never equal 0, so the only thing we have to worry about is setting this part equal to 0. So we set 1 minus x equal to 0, we end up getting x equal to 1. Put it on the number line. Look at what our derivative is doing. So, and it's definitely easiest to look at the factored form of your derivative. So here we're looking at f prime being 3e to the negative x times 1 minus x. Pick a number bigger than 1 like 5. 1 plus negative 5 is negative. 3e to the anything is positive. A negative times a positive is negative. Over on the other side of 1 like it's 0. 3e to the 0 is positive. 1 plus 0 is positive. The whole thing's positive. So our function is increasing, then decreasing, which means we definitely get to have a relative maximum at x equal to 1, y equal to f of 1. And we might as well plug it in here and see y is going to be f of 1, which is 3 times 1 times e to the negative 1, which I would probably write as 3 divided by e, which is not too far from 1, right? E is about 2.7. 3 divided by 2.7 is a little bit bigger than 1. Let's look at the next part. What's the next part? Oh, the second derivative stuff. So we take our first derivative, which I might rewrite as 3e to the negative x minus 3x e to the negative x. Or, I don't know. I don't know which way is better. It's kind of a matter of opinion. Do I want to take the derivative of this, or do I want to take the derivative of this? Either way, kind of. I'm going to do this because I wrote it already. So let's see. So my f double prime of x is going to be the derivative of 3e to the negative x is 3e to the negative x times negative 1. And then here I have a minus, and then I'm going to take the derivative of 3x e to the negative x. Oh, here's why I like doing it this way. Yeah. Minus the product rule for the derivative of 3x e to the negative x, which I just did in the previous problem. So don't do more work than you have to. Use the work you've already done. The derivative of 3x e to the negative x is exactly 3e to the negative x minus 3x e to the negative x. So putting it all together, I have a negative 3 e to the negative x minus 3 e to the negative x, so a minus 6 e to the negative x. Minus the minus is plus 3x e to the negative x. This happens a lot when you have like a product rule with an e to the x or an e to the something, is that when you take the second derivative, part of your first derivative ends up, or part of your second derivative ends up being the first derivative you already took. So you kind of reuse the work you've already done. Let's see. Setting this equal to 0 and factoring out a 3e to the negative x, I'm left with a negative 2 here and a plus x over here. So I end up getting a critical value of x equal to positive 2. Putting that on my second derivative number line, we're going to see a similar result. Pick a number bigger than 2, like 5. Negative 2 plus 5 is positive. This part's always positive. Positive over here. Pick a number like 0. Negative 2 plus 0 is negative. That part's always positive. So we see that we are concave down and then concave up. So we definitely do have an inflection point at x equal to 2, y equal to f of 2, which is going to be plugging into up here. 3 times 2 is 6 times e to the negative second, or 6 over e squared. I'll remind you that e squared's around 8, so 6 over e squared is a little bit less than 1, which is good because our relative maximum had a y value of a little bit bigger than 1. So anything kind of to either side of that should be having y values that are less than that relative maximum value. All right, the last part is to put it all together on the graph. And this will come back to the horizontal asymptote that we kind of skipped over before, but not really. So putting it all on the graph, let's see, we have our intercept of 0, 0, our no vertical asymptote. We'll talk about the horizontal asymptote in a minute. My first derivative stuff, I have a relative maximum at x is 1 and y is 3 over e. So it's kind of like this. So here's my relative maximum of 1 comma 3 over e. And I'm going to use my first derivative sign chart to help me graph this. So I can see that it's going to be increasing left of this point, decreasing after. So I know I'm going to be going up, 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 down, 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 down. So I think I can do a pretty good job of graphing this. I'm going to go up like this. I'm going to max out right there. Now, when I turn around, let's be thoughtful before we do it. I don't want to just go down like this for a couple reasons. One, I know I'm not concave down the rest of the way. 2, I know I don't have another x-intercept. I shouldn't be ever crossing the x-axis if I don't have an x-intercept. So what happens here is we're kind of stuck. We are forced to always be decreasing after this, but we can't ever cross the x-axis, which typically means we end up having a horizontal asymptote at y equals 0 the x-axis. So that's what's happening here. We definitely decrease, and then we kind of change directions and flatten out. So we get closer and closer to our horizontal asymptote. So sometimes, especially with these like e to the x graphs, you can kind of figure out what the horizontal asymptote is going to be just because you're stuck having it. And we do have our inflection point over here at 2 comma 2 over e squared. And there's your whole graph. I guess I could label my horizontal asymptote as y equal to 0. I don't want to do this next one because I think it's a little too repetitive, but I will encourage all of you on your own. I would say a good problem to work on, which is similar, but has a little bit more going on, is to graph f of x equal to x to the 4th times e to the negative x. And I will say this graph is nice because all of the critical points are nice integer values. So it's a good example of a graph that's worthwhile. I would encourage, not right now, but on your own, I would say this is a good use of your time to find all the things. Intercepts, the asymptotes, or wait for the asymptotes. Definitely the first derivative critical values, the second derivative critical values, and graph the whole thing. It's not too terrible at all. And then check your work on Desmos. I would. Let's look at 2 other examples here. Yeah, 2 other examples. Yes. Where'd you go? Yeah, let's do that one first. Well, maybe. You'll have to tell me, actually. Sure. So let me ask you a question. Have you guys looked at a graph? Have you actually seen the graph of natural log of x over x? I ask because it's often a common example. Like I'm not expecting that you've seen it, but I wouldn't be surprised if you hadn't. As far as I can tell, the answer is no. Okay, let's do it. And in this example, I should be smart and do it the way your teacher says, which is I should first think about the domain. What I really should say is you shouldn't think about the domain unless you need to, which means I guess you should always think about it. Like, okay, well, does the domain matter here? And it definitely does matter here, right? First of all, x can't be zero for two reasons, actually. We can't divide by zero and we can't take the natural log of zero. And also, our natural log function means that here our domain is that x has to be greater than zero. So we're already very limited in what we can work with. Let's find, let's talk about the intercepts. So y-intercept, we shouldn't even talk about because we can't have one because that can't be zero, right? You find the y-intercept by setting x equal to zero, but we're not allowed to. So not possible. How about the x-intercepts? Well, we're going to set the whole thing equal to zero. When you set the whole thing equal to zero, you're really just setting when it's a I don't want to say rational function because it's not a rational function because it's not a polynomial divided by a polynomial. When you have some sort of quotient thing like this, we just set the top equal to zero. So if I set the natural log of x equal to zero, what's my only solution? Right? Natural log of 1 is equal to 0. So we do get an x-intercept. It's 1 comma 0. Great. Let's let's talk about the asymptotes. So vertical asymptotes. Well, it seems like there's a candidate here. X equal to 0? Maybe? Let's see what happens. So what does it mean to really be a vertical asymptote? I know it means typically we're dividing by 0, but the actual kind of more definition way of saying it is if you think something's a vertical asymptote, like x equal to 1 or x equal to 5 or x equal to 7, then the limit as x approaches that number should be some sort of infinity. At least from one side. It doesn't have to be from both sides, but at least from one side, which is good because we only have one side here anyway. We can only approach 0 from the right. We can't approach 0 from the left. So let's ask ourselves what happens as x approaches 0 from the right of the natural log of x divided by x. Well, the bottom is certainly getting very, very small. How about the numerator? What happens to the natural log function as x gets really, really, really close to 0? Negative infinity. I don't know if I've said this before. And my hand is not the best because I'm 47 years old. But if you look at your right hand, have I said this before? Cool. Look at your right hand. Down your pencil if you're right-handed. Look at your right hand. You kind of have a natural log function line right there, which is not easy to see on my hand. And you kind of have an e to the x function right there. It's kind of useful. So the natural log function, if you graph it, just as a real reminder here, natural log of x looks like that. And oh yeah, as x gets closer and closer to 0 from the right, the y values go down, 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 down to negative infinity. So we have a negative infinity divided by a positive 0. This is not an indeterminate form. We know what this is doing. You have a really giant negative number divided by a super small positive number. It's going to overall be negative and super giant, right? Giant number divided by tiny number is giant in both ways. So this is going to be negative infinity. So it looks like we do have a vertical asymptote at x equals 0. Cool. Horizontal asymptotes. Well, this is definitely one that's harder to justify. If you look as x goes to infinity of the natural log of x over x, this is really like a prime example of where you would use L'Hopital's rule. let's go ahead and talk about it because it's not that hard to understand here. So, if you were to plug in infinity, the bottom is certainly getting infinitely large. How about the top? Does natural log of x plateau? Does it stop getting bigger? No. It does slow down quite a bit, but it doesn't have any horizontal asymptote, right? The natural log function, albeit very slowly, does get larger and larger and larger and larger forever and ever and ever. So as x goes to infinity, the natural log of x also goes to infinity. And this is kind of the essence of why you might need L'Hopital's rule. Because what L'Hopital's rule says is if you have one of these specific indeterminate forms that's either infinity over infinity or 0 divided by 0. There are other forms, but you can't use it on those until you've massaged them to look like one of these. But once you have something like this, you can then say, well, this limit is equal to the limit still as x goes to infinity, but then you get to take the derivative of the numerator part and the derivative of the denominator part. The derivative of the natural log of x is 1 over x. The derivative of x is 1. And now you can more easily say, oh yeah, as x goes to infinity, 1 over x goes to 0. And we get 0. So your horizontal asymptote will be y equals 0. I will also mention, you could totally justify this one kind of the same way we did the previous one. That even though it's infinity over infinity, the top infinity is much smaller than the bottom infinity. For example, if you plug in something like 1,000, natural log of 1,000 is, I don't know, probably like on the order of 10, probably less actually. But so if you plug in 1,000, you get something about like 10 over 1,000. That's tiny. So this fraction is definitely getting smaller and smaller and smaller. All right. So then the other parts, the derivative things. First derivative stuff. All right. So I got to use the quotient rule here. My function was the natural log of x over x. Maybe I should write that down again. My first derivative is going to be the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. Definitely want to simplify this. We're going to rewrite it as 1 minus the natural log of x over x squared. We're going to set it equal to 0 / see where it's undefined. Remembering that our domain is limited, right? We don't even want to think of x being negative or equal to 0. Although 0, we should probably think about because it's on the edge. So what makes this undefined? Definitely x equal to 0, which isn't surprising because it wasn't in the domain anyway. What makes it equal to 0? Well, if we set 1 minus natural log of x, the top part equal to 0, we get 1 equal to the natural log of x, or e to the 1 equals x. So x equals e. When we draw the number line for our first derivative, we shouldn't draw the whole number line. This thing isn't defined on half of it. So here's the number line we're going to draw. We're going to start at 0, but it's not defined even at 0. And then we're going to go only to the right. And then if you really want to be, you could say, I even know I have a vertical asymptote at 0. Cool. So then, this is an excellent thing to do here. So we want to know if our derivative is positive or negative over here to the right of e. Don't plug in 3. I don't know what natural log of 3 is, although you could probably just plug in something that's easy to take the natural log of, like e squared. If you plug in e squared, you're going to get, let's see, 1 minus the natural log of e squared is 2, divided by e squared squared. That's definitely a negative over a positive. That's negative. It's negative over here. What are you going to plug in between 0 and e? I have 2 suggestions. Either the square root of e, which is e to the 1/2, or 1 over e, which is e to the negative 1. Those are both valid choices between 0 and e. Or between 0 and... Oh, or you can pick the smart choice. 1. You can pick 1. It's a much easier choice to pick than e to the -1 or e, but those are also good choices. If we pick 1, natural log of 1 is 0, 1 minus 0 is positive, 1 squared is positive, it's positive over here. So our function is increasing, then decreasing. Now, here's what I would check just to make sure I wasn't on the wrong side of things. If it's increasing on the right side of a vertical asymptote, it better have been down to negative infinity and then going up, 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 up. Let's see, let's check. Was our vertical asymptote? Yes, okay, good. It was going to negative infinity, so I feel all right about that. But right, it has to match up. Okay, so we have a relative maximum at x equal to e, y equal to f of e, which is the natural log of e divided by e, which is 1 over e, which is about 0.3. Comes up often enough that it's worth knowing it's about 0.3. All right, and then we do the second, right? It's just the same stuff over and over again. But it's good practice. So second derivative stuff, same sort of deal. Look at your simplified first derivative and apply the quotient rule again. So it's going to be f double prime of x equal to the bottom times the derivative of the top, which is 0 minus 1 over x, minus the top, 1 minus the natural log of x, times the derivative of the bottom, which is 2x, all divided by the denominator squared, which is x to the fourth. Now, you all should know that when I simplify this, I should end up getting x to what power in the denominator? Show me on your fingers. What power should I get after I simplify in the denominator? I want one more finger. This many. 3, right? I've said this a number of times that when you do the quotient rule repeatedly, the power in your denominator, after you simplify, always ends up increasing by 1. So if we went from something with divided by x squared, we should eventually end up with something divided by x cubed. Always true. So even though the quotient rule makes you square your denominator, what it actually does after you simplify is it always just increases the power of your denominator by 1. Always. It's kind of weird, but it's kind of neat. So simplifying here, the x squared times -1 over x is going to give me a negative x. And then, yeah. I don't really want to, I guess I should, let's write this as minus 2x times 1 minus natural log of x. Maybe I should have factored out the x right there. Let's factor out the x here. Factoring out an x, I'm left with a -1 minus 2 times 1 minus natural log of x. All divided by x to the fourth. Oh, yeah. An x cancels here, and x cancels here. Now let's distribute the -2 on top. I've got a -1. A minus 2 times 1 is -2. A minus 2 times negative natural log of x is a plus 2 natural log of x divided by x cubed. Finally, the last simplification, and let's rewrite it. If we can, if you've got like negative things and positive things, we usually prefer to write the positive thing first. You could write -3 plus 2 natural log of x, or you could write more typically 2 natural log of x minus 3 over x cubed. Oh, okay, we're going to set that equal to 0 and see what comes up. We know that 0 is going to make it undefined. So if we set this equal to 0, we set the top part equal to 0, and we get kind of an unsatisfying answer. We get 2 natural log of x equal to 3. The natural log of x is equal to 3 over 2. So x is going to equal e to the 3 over 2 power, which is certainly bigger than e to the 1. So our second derivative critical point here is occurring to the right of our first derivative critical point. So let's make the sign chart. So we have our e to the 3 halves over here. We've got a vertical asymptote over here. And same idea. We're taking our second derivative, apologies, looking at kind of the form that's easiest to plug into, and being smarter this time and picking something smaller than e to the 3 halves, like 1. Plug in 1, 2 natural log of 1 is 0, 0 minus 3 is negative, bottom's positive, the whole thing is negative over here. Picking something larger than e to the 3 halves, like e squared, by plugging in e squared, the natural log of e squared is 2, 2 times 2 is 4, 4 minus 3 is positive. The bottom is positive. The whole thing is positive. So it's concave up, then concave down. We have an inflection point at x equal to e to the 3 halves, y equal to f of e to the 3 halves. Okay, so depending on how, yeah, question. Did I draw them wrong? I totally drew them wrong. How did I, wow. Gosh, time to get old sometimes. Okay, there we go. Thank you so much. Interesting. Yeah. Yeah, concave up would have been a challenge there with the vertical asymptote going the way it goes. Sometimes, depending on how terrible your second derivative critical points are, on a graph, if I was low on time on a test or just didn't feel like it, I might label my point as e to the 3 halves, comma, f of e to the 3 halves, as opposed to actually plugging it and finding it. We can probably find it here though, because our function was the natural log of x over x. Yeah, that's not too bad. It's going to be the natural log of e to the 3 halves divided by e to the 3 halves, or 3 over 2 e to the 3 halves. I have no idea what that's approximately equal to. I don't really need to know. Let's graph it and see what happens. Okay, putting all the pieces together. We know that we have an intercept at 1, an x-intercept, I should say. And then we know that we have a vertical asymptote like this. So what other points do I have here? I have my vertical asymptote there. I have a horizontal asymptote, but that's not something I can really graph either. And then I had my first derivative stuff. So I have a relative maximum at E, which is about right here. And it was E comma 1 over E. I'm going to exaggerate my y-axis a bit. It's fine. So here's what we know. Looking at our first derivative sign chart. We are increasing until we get to that point there, decreasing afterwards. And we can't cross the x-axis except for right there. So it's going to look like this. And then we decrease, and then we turn around. And my inflection point's right about there. Let's say that that's my e to the 3 over 2. So here's my e comma 1 over e. Here's my e to the 3 over 2 comma 3 over 2 e to the 3 over 2. Horizontal asymptote, y equals 0. Vertical asymptote, x equals 0. Oh, sorry, you can't see all that. All these. Nothing on the left side of the graph, right? There's nothing where x is negative. So graphing, it doesn't have to be perfect. You do have to label. I think you should either label the points or make it clear what your points are, right? I'm definitely trying to make, and definitely doesn't have to be the scale unless she just says it does, but it really shouldn't have to be, right? My 1 over e here, which is about 0.3, it looks like it's bigger than my 1 here. That's fine. Nobody cares as long as the graph looks reasonable. All right, I think that's enough graphing stuff. You can graph till the cows come home, right? Graphing, you just keep graphing. It is good to practice. I definitely recommend practicing graphing things and then looking at the graph on Desmos. I think that is a very, very useful way of being able to see how things look. But I definitely think you want to practice trying it on your own before you just look at what the graph on Desmos is. Also, something I don't remember if I mentioned this last or not, but on Desmos, if you label your graphs appropriately, you can get the derivative without doing any work. So in case you didn't know, why don't you give me the graphing calculator automatically? That's what I want. There you go. Cool. So just as a fun kind of fact here, if I wanted to graph something like y equals, sorry, not y, let's call it f of x equals x squared times e to the negative x. There's what the graph looks like. And if you wanted, there's what the derivative looks like. Kind of cool. And if you wanted, there's what the second derivative looks like. So what this tells me, if I turn this one off for a second, this one tells me that my first derivative is negative left of 0, positive between 0 and 2, And I think it crosses again somewhere over here. It's hard to tell. But it definitely gives you, it can help you kind of have an idea of if you're finding the right critical points, right? If you're saying your derivative equal to zero and solving, you can then look at the graph of the derivative and be like, well, did I actually get the same critical points? It's kind of neat. Without using the internet to tell you what the derivative actually is. You just like, I found the derivative myself. I think I'm right, but I'm not going to check. I'm going to find my critical points, and I am going to check to see if my critical points are right. And if they're not, then you go back and be like, well, maybe I made a mistake with the derivative somewhere. All right. Let's go ahead and move forward and talk about L'Hopital's rule because I do believe your instructor, yeah, L'Hopital's rule before optimization. Yeah, question. Oh, thank you. Yes. I was letting it dry because it's a little water. Oh my gosh, can I get, maybe we'll stop. Okay, there we go. So let's talk about L'Hopital's rule. Um, doesn't really matter, but it's not pronounced La Hospital. It's L'Hopital. I would encourage you to say it correctly just because it sounds terrible if you say it wrong. So here's the general idea. If both f of x and g of x are differentiable functions, and here's what actually matters. If the limit as x approaches a of f of x over g of x is equal to either 0 over 0 or some sort of infinity over some sort of infinity, the infinities do not have to match here. It could be a positive infinity over a negative infinity, a positive over a positive, a negative over a negative, right? They don't have to be the same type. Some sort of infinity over some sort of infinity. So if your limit is one of these two types of indeterminate forms, then we can say that the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x. With an asterisk, provided that this limit actually exists. So if you do L'Hopital's rule and the thing you get is something that has a limit that doesn't exist, you got to go back to the drawing board. I want to be extra clear. I know I said it before, I'm going to say it again. It has to be these indeterminate form types, either 0 divided by 0 or infinity divided by infinity, which I will point out were limits we saw back in the beginning of the course, right? We saw plenty of 0 over 0 and infinity over infinity limits. In fact, I think it's kind of worth starting off with some examples we saw before. So let's look at an example that we could do a different way. Say like the limit as x approaches 3 of x squared minus 5x plus 6 divided by x squared minus 9. And we'll do this both ways. So let's do it the old way, where we factor and cancel, right? Oh, I should stop myself. Is it even a 0 over 0 type? Let's double check. I plug in 3, I get 9 minus 15 plus 6, which is 0. I get 9 minus, yep, it's a 0 over 0 type. So since this is a 0 over 0 type, now we can do something. And the old way would have been to have factored it. So if the limit as x approaches 3, we have on top x minus 3 times x minus 2. On the bottom, we have x minus 3 times x plus 3. The x minus 3's divide to 1. And now you can plug in the 3 for the remaining x's and get 3 minus 2 over 3 plus 3, which is 1 over 6. Or we can use this new thing, L'Hopital's rule. Now, when you use L'Hopital's rule, I encourage you to say that your limit is equal to and write an L apostrophe H above the equal sign in the step where you're using L'Hopital's rule. So now watch what I'm going to write. I'm going to write the limit. You have to still write the limit. It's not L'Hopital's rule if you're not writing a limit. As x approaches 3, derivative of the top, 2x minus 5, derivative of the bottom, 2x. That's it, right? So in this step from here to here, I've used L'Hopital's rule. I had a 0 over 0 type, and you took the derivative of the top, derivative of the bottom to the limit of that. And now I ask myself, can I just plug in the 3? So if I plug in 3, I get 6 minus 5 over 2 times 3. I get 1 over 6. The same answer. So the thing about limits is it doesn't matter which way you do it. If you can do it that way, you should get the same answer as someone else that did it a different way. So either way we do this, we get the same result. Great, we should. Let's look at another example of something we already knew how to do. Let's look at something like, sure. Let's try the limit as x approaches infinity of 6x squared plus 4x plus 3 over 3x squared plus x plus 5. And back in the beginning of the quarter, we would have dealt with a limit like this by dividing everything by the highest power of x in the denominator. So we divide everything by x squared. We're going to get the limit as x goes to infinity of, let's see, 6x squared over x squared is 6. 4x over x squared is 4 over x. 3 over x squared is 3 over x squared. 3x squared over x squared is 3. X over x squared is 1 over x. And 5 over x squared is 5 over x squared. And then as x gets really, really big, this part goes to 0. This part goes to 0. All the parts we were dividing by x to some power go to 0. So we're left with 6 plus 0 plus 0 over 3 plus 0 plus 0, which is 2. Or L'Hopital's rule. So if we do this one here, it's going to be equal to, I should point, again, I'm getting a little ahead of myself here, apologies. Before I did any of this, I should have verified I had an indeterminate form. If I plug in infinity for x, I get infinity plus 3 over infinity plus 5. So I do definitely get an infinity over infinity type, meaning I'm allowed to use L'Hopital's rule. So then using L'Hopital's rule, I'm going to get the limit as x goes to infinity of the derivative of the top, which is, let's see, 12x plus 4 plus 0, over the derivative of the bottom, which is 6x plus 1 plus 0. And now at this point, I still have an indeterminate form. If I plug in infinity for x, I still get infinity over infinity. We know what that means. I use L'Hopital's rule again. Sometimes you use L'Hopital's rule like 3 or 4 times in a row because you keep getting a 0 over 0 or infinity over infinity type. Sometimes that's not good. Most of the time it's fine. So using L'Hopital's rule another time, I still have the limit as x goes to infinity. The derivative of the top is 12. The derivative of the bottom is 6. 12 divided by 6 is 2, and the limit of a constant is just that constant, so we get 2. The same answer we got over here. Great. That's what we expected. So we definitely can see that for some examples we already knew about, L'Hopital's rule definitely works. Let's talk about some examples where you can't do it a different way typically. In fact, what was the example I said we were going to look at again? Where'd you go? Sorry, 1 second. Remember what it was exactly. I think it was x e to the negative x. Yeah. Oh, 3x e to the negative x. Yeah. So what about the limit as x goes to infinity of 3x e to the negative x? Well, this actually isn't written in the right sort of form, right? I pointed out last time that this is a really big number times a really small number. But we know we can't use L'Hopital's rule at all if you don't have a fraction, right? You just cannot. You have to have a fraction, specifically a zero over zero type or infinity over infinity. I'm gonna say it like 1,000 times. This is gonna get so repetitive, but you have to have that. I've seen too many people try to use L'Hopital's rule on something like that before doing anything, where they just said, "Oh, L'Hopital's rule, take the derivative." No, we cannot just take the derivative. It is a quotient, and you take the derivative of the top and separately the derivative of the bottom. No quotient rule unless you have like a fraction and a fraction. But typically, you're not using it's just like whatever's in top, take its derivative. Whatever's bottom, take its derivative. So here we're going to rewrite it. We're going to rewrite it as the limit as x goes to infinity of. You can kind of go either way, but the general kind of idea you want to keep in mind is we would like both pieces to be relatively easy to differentiate. I should write it as 3x over e to the x. I will point out, you could also, although this would be much worse, you could write it as the limit as x goes to infinity. You could leave the e to the negative x on top and put the 3x in the denominator as 1 over 3x, or if you prefer 3x to the negative first. This seems much worse. I don't want to take the derivative of that or really the derivative of that. You want the things to be kind of nicer than if possible. So pick the nicer looking thing. Both of these are indeterminate forms. Here, if x is going to infinity, the top is going to 3 times infinity, the bottom is going to e to the infinity. It's an infinity over infinity. Over here, e to the negative infinity is going to 0. 1 over infinity is going to 0. So either way you rewrite it, it will be an indeterminate form if you were starting with an infinity times a 0. Pick the easier way. So if I write this, it's going to be the limit as x. Oh, if I'm using L'Hopital's rule, it's the limit as x goes to infinity of the derivative of 3x, which is 3, divided by the derivative of e to the x, which is e to the x. So that's going to be 3 over something infinitely large. It's no longer an indeterminate form, right? It's a not infinity. It's a constant divided by infinity. That's going to be super duper small. That's going to be 0. The fact that the derivative of e to the x is just e to the x kind of tells us a little bit more about kind of how polynomials and exponential functions compare to each other. I could have picked a much higher power of x. For example, I could have asked something like, what's the limit as x goes to infinity of x to the 4th power divided by e to the x? Well, it's starting off as an infinity over infinity indeterminate form. If I use L'Hopital's rule, the denominator is never going to end up changing. But the numerator is. So let's see what happens here. If I use L'Hopital's rule, it's going to be the limit as x goes to infinity of the derivative of the top divided by the derivative of the bottom, which is still an indeterminate form. And if I do it again, it'll be the limit, you should write the limit every time, of 12x squared over e to the x. Still infinity over infinity. We do it again. The limit as x goes to infinity of 24x to the 1st over e to the x. Still infinity over infinity. You do it one more time. The limit as x goes to infinity of 24 over e to the x. And now finally, it's not an indeterminate form. It's a constant divided by something that's getting infinitely large, which is going to go to 0. And this would have been true whether I started with x to the 4th power or x to the 400th power, or x to any positive integer power. So what this tells us really is that e to the x will eventually overpower or exceed any x to the p, where p is some positive integer. And it doesn't have to be an integer, actually. Well, but it helps if it is. There's definitely a question in the textbook that says, it's like something like find the limit as x goes to infinity of x to the 100th power over e to the x. And you know what the answer is going to be already. You know it's going to be e to the 0. Now, I will point out, just because I think it's kind of worthwhile, if you did the L'Hopital's rule, let's see, how many we did it for x to the 4th, we had to do it 1, 2, 3, 4 times. So we did this L'Hopital's rule 100 times. We'd end up with the limit as x goes to infinity of, we'd have e to the x on the bottom. What would we have on top? Well, I should say, what constant would we have on top? Well, first we'd have 100 times 99 times 98. Just like this was 4 times 3 times 2 times 1. This would be 100 times 99 times 98 times, oh my God. There's a better way to write that. 100 factorial. If this is not familiar notation, that's totally fine. But all that, but it will become more familiar because we do definitely use it, especially in 21C. We definitely use this factorial notation quite a bit. But first of all, two things. I'll say that number there, even though it's really big, right? 100 times 99 times 98 all the way down to 1. This is a big number. It's still a constant. And really big constants are still nowhere near as large as infinity. It's dwarfed by infinity. This limit of a constant divided by something infinitely large is still going to be 0. But just to make sure everyone's clear, 100 factorial just means 100 times 99 times 98 times 97, all the way through every integer, all the way down to 3 times 2 times 1. Just so you all know. Because this notation gets used quite frequently. Let's see, what other examples do I have? What time is it? I got 12 minutes. Okay, let's look at a few more examples. Let's say we wanted to find, I feel like I had, let me look back and see if I have this example I really want. Sure, you're fine. Okay. Yeah, let's look at this guy. Ooh, here's a blast from the past. The limit as x goes to 0 of sine of x over x. What's that one equal to? Everybody should be able to tell me what this limit is equal to without doing any work. It's a 1, right? I know it's been a while, but that's definitely 1. But now we can use L'Hopital's rule to see it. Let's see if we use L'Hopital's rule. We get the limit as x goes to 0. The derivative of sine of x is cosine of x. The derivative of x is 1. Plugging in 0, you get cosine of 0 over 1, which is just 1. And this even works for other things. Like now instead of using like the wish method we did before, where we like would multiply, where there's a bunch of fractions, to do something like the limit as x goes to 0 of sine of 6x over 9x. Instead of kind of writing out a bunch of stuff, you can still do this using L'Hopital's rule. Say it's the limit as x goes to 0 of the derivative of sine of 6x, which is cosine of 6x times 6, over the derivative of 9x, which is 9. And you plug in 0, you get cosine of 0, which is 1, times 6 over 9. That's going to be 6 over 9, which is 2 over 3. A warning. L'Hopital's rule is a very powerful tool. Sometimes it's still not the best tool to use. For example, how terrible do I want to make this? Sure, we'll make it medium terrible. Let's say we had the limit as x goes to 0 of sine squared of 2x over 3x squared, which is definitely a 0 over 0 type. And again, I've been, unfortunately, a little bit too lax here. I should have pointed out in the previous two problems that sine of x over x is a 0 over 0 type, sine of 6 over 9. You definitely have to make sure, at least internally, that you have something you're allowed to use L'Hopital's rule on. Because occasionally there'll be something you can't. Now here, you might not want to write this down because it's going to get ugly. And I'm going to tell you, it's probably not the way I would usually do this problem, but I want you to really have evidence that L'Hopital's rule isn't always great to use, even if it works. Sometimes it doesn't even work, even though it's still applicable. We'll get there in a second. So if I use L'Hopital's rule, I get the limit as x goes to 0. This one might not be too terrible. Let's find out. I have some stuff squared. The derivative of something squared is 2 times my something to the first power. So 2 times sine of 2x to the first power times the derivative of my stuff. The derivative of sine of 2x is cosine of 2x times 2. At the bottom, my 3x squared derivative is 6x. Okay. So I could simplify it a little bit. A 2 can cancel here and a 2 can cancel here. But now I'm trying to take the derivative of the limit as x goes to 0 of 2 sine of 2x times cosine of 2x divided by 3x. I'm going to have to use the product rule on top. Okay, so let's see. Well, whoa, I should stop. Is it still a 0 over 0? If I plug in 0 for x, what do I get? Let's see. I get sine of 0, which is 0, times, it doesn't matter because it's still 0 on top, divided by 0 on the bottom. So yes, it's 0 over 0. So we use L'Hopital's rule again, and things start to get a little bit ugly. Limit as x goes to 0. Let's see, I'm going to leave the 2 and the 3 out in front. The derivative of sine of 2x times cosine of 2x, I have to use the product rule. So it's going to be cosine of 2x times 2 times cosine of 2x plus sine of 2x times the derivative of cosine of 2x, which is negative sine of 2x times another 2. On the bottom, I get 3 times 1. Oh, that's kind of a lot. Not totally unreasonable, but on the edge of unreasonable. If we plug in 0 now, well, first of all, notice I didn't even think about whether or not I could plug in 0 because my denominator is no longer a 0 or an infinity, right? This is definitely not an indeterminate form. I don't have a 0 over 0 or infinity over infinity. So I'm just going to jump straight to plugging in and seeing what I get. So I'm going to get on top 2 times cosine of 0 is 1 times cosine of 0 is 1 times 2. So you get 1 times 2 times 1. Well, sine of 0 is 0. I don't even need to think about the rest because it's 0 times whatever. All divided by 3, I get 2 times 2 over 3, which is 4/3. I wouldn't do it this way. I would go back to the old school way of doing it, where we broke it apart into pieces and tried to look for sine of something over the same something. I think it is better to do it as the limit as x goes to 0. Instead of writing sine squared of 2x over 3x squared, I'm going to write sine of 2x over blank times sine of 2x over blank times blank over 3x squared. And then what do I wish I had down here? 2x. I want one there, so I need one there. I want one there, so I need one there. The limit of this is 1. The limit of this is 1. Here the x's cancel, and you get 2 times 2 over 3. So you end up getting exactly 1 times 4/3, which is 4/3. Seems a lot easier to me to do it that way. Not unreasonable if you have sine squared, but I will tell you, I've done it before. I will not do it here because it is terrible. If it was something like the limit as x goes to 0 of sine cubed of 4x over 5x cubed, the first step's okay. The second step's pretty gross. The third step is ridiculously terrible. Don't do it. Do not use L'Hopital's rule, even though you could. Let me give you one more example of a place where L'Hopital. We're going to talk about L'Hopital again on Thursday, so I feel like because we'll get to the other indeterminate forms on Thursday. Let me give you one more example of a place where it's dicey, if I can remember what it is. I believe it's the limit as x goes to. Now I'm completely forgetting the example I had in my head. Give me 1 second. Let's see. It's that. It's that. I think it's that. I think it's x over the square root of x squared plus it doesn't really matter, but let's try that. As x goes to infinity. So first of all, I'll point out this is an infinity over infinity form. bottom's going to infinity, the top's going to infinity. So we're going to use L'Hopital's rule. And if I'm going to use L'Hopital's rule, I might want to rewrite it or at least rethink of it as x over x squared plus 1 to the 1/2 power to make my life a bit easier. Oh yeah, we should do that one too. So in this case, if we use L'Hopital's rule, look what happens. I get the limit as x goes to infinity. The derivative of the top is 1. The derivative of the bottom is 1/2 times x squared plus 1 to the negative 1/2 times the derivative of the inside, which is 2x. It is usually not a bad idea to simplify things before you try to see if you can use L'Hopital's rule again. So let's see what we've got here. We've got the limit as x goes to infinity of 1 on top. The 2's cancel. I have x times x squared plus 1 to the negative 1/2. Or if I bring this up to the top, I have the limit as x goes to infinity of x squared plus 1 to the 1/2 power over x. That's kind of weird. It looks like my bottom and my top just switch places. It's still infinity over infinity. So I guess we do it again. So we use L'Hopital's rule again. Prepare for bad news. If the limit as x goes to infinity, the derivative of the bottom is going to be 1. The derivative of the top is going to be 1/2 times x squared plus 1 to the negative 1/2 times 2x. And if you simplify this, you're going to get to back exactly where you started. It's going to be the limit as x goes to infinity of the 2's cancel. You get x on top, and the x squared plus 1 to the negative 1/2 comes down to the bottom as x squared plus 1 to the 1/2. All that work for literally nothing. Well, maybe one thing. So here's kind of an interesting fact. Let's get to the result before we say the fun fact. So this one, even though L'Hopital's rule is applicable, it doesn't get you anywhere. You literally cannot find the answer using L'Hopital's rule. Maybe you could after we talk about what the answer is. So what do we do instead? We use our old school methods. I'm going to factor out x squared from the bottom inside the square root. So I'm going to rewrite this as the limit as x goes to infinity of x over, watch this, the square root of x squared times parentheses 1 plus 1 over x squared. And then we pull out the x squared. The limit as x goes to infinity. On top we have x. On the bottom, what's the square root of x squared going to be? In this case, just x. In general, the absolute value of x. But since x is positive, we can say it's just x. Okay, check it out. The x's cancel. You get 1. You have the limit as x goes to infinity of 1 over the square root of 1 plus 1 over x squared, which ends up being 1 over the square root of 1 plus 0, which is just 1. Here's an interesting piece of information, I think. We took a limit, used L'Hopital's rule, and the limit of this expression is equal to the limit of the reciprocal of that expression. If the limit were to exist, what are the only numbers, there are 2 of them, that are equal to their own reciprocal? Well, what's one of them? 1, right? What's 1 over 1? Also 1. What's the other answer to that question? -1, right? 1 divided by -1 is also -1. So if you use L'Hopital's rule and you end up getting the limit is equal to exactly the limit of its reciprocal, that's a good sign that your answer is either 1 or -1. It's kind of weird, but it's kind of neat. But again, we shouldn't really use L'Hopital's rule here. And I will stop talking because it's 2:30. All right, on Thursday, we'll talk more about L'Hopital's rule. We'll talk about all the various indeterminate forms, like infinity times 0, or infinity minus infinity, or infinity to the 0th power, or 1 to the infinitieth power, or whatever the third one is, so 0 to the 0th power. We'll talk about how you can know if it's an indeterminate form. And then optimization after that. Then that's it. You're done with 21A. I'll have office hours over in the usual place, as usual. Nice.